It is my real pleasure to have Domenico Prattichizzo as the keynote speaker today. Domenico is most well known for his work in haptics and his earlier work in grasping. Domenico served the community in various distinguished capacities on the editorial boards on society's most important journals, Transaction on Haptics and Transaction on Robotics and Automation. And he also led large-scale EU robotics projects. And today, Domenico is going to tell us his recent work on wearable haptics, specifically what he calls the sixth finger, which binds together his interest both in haptics and in grasping. Domenico.
Thank you for the introduction. So our interest is of my research group. I will talk mainly about the work of my lab on wearable haptics and wearable robotics. So we are strongly interested in haptics, touch, grasping, and interaction and wearability. Our vision, it will be clear in the next slide, is to create new embodied sensorimotor interfaces. For sensorimotor interface, I mean something that can track our limbs and also actuate forces on our limbs to guide our limbs somewhere. To create new paradigms of integration. Haptics. This is standard technology for haptics. You see on the left a grounded device that is able to provide force feedback on the hand, but is grounded actually. On the other side of the slide, you will see an exoskeleton. The exoskeleton is grounded not on the desk. What we wanted to do in our research is to create something different that we call highly wearable haptics. And this is inspired by the idea of the Sony Walkman device. You saw the Sony Walkman device was very famous in 1980 because it was the first device that was able to provide some information on our auditory modality, but while it's really wearable. So I was not able to listen my music in my room anymore, but now while walking. So we wanted to do the same with haptics. So I want to feel something while walking with the haptic interface. And we tried to develop this device. This is the device that we developed in 2013. It's a parallel robot which moves the cable with the three motors, three cables. It moves the platform, span, tilt, and wearable indeed. This is something that we created with the idea of moving the grounding part from the ground, from the forearm to the nail, basically. And this is what we realized recently. Well, this is actually the last demo that we did at World Haptics conference in Chicago in 2015, where you can see that our wearable device was able to provide the tangent plane to the sphere, and we were really able to understand how good was the interaction in a wearable way, because the platform was doing a pan, tilt, and squeeze, and providing force feedback at the fingertip. And it was clear that we were doing this in a very wearable way. One of the problems here was to show the part while moving. So one of the problems in haptics is the tracking, basically. On the other side, you can see that there are many interesting control problems here, because you have to control the device. One of the big problems is the tracking, and then you have to control the plate, the position of the plate, according to the surface. And this is an example of position control interaction of our device. We have also force-controlled device by putting force sensors on the platform to show compliance of the object in this area. Another important thing here is that with the grounded haptics, it was really difficult to realize multiple finger interaction, while it is very easy with this wearable device that goes to the cutaneous interface, to the cutaneous interaction. So it's not involving actually the muscles. So it's very to show multiple finger interaction, and so we are able to interact with the virtual environment with 5 fingers. These are demos that we showed at SIGGRAPH in the last 2 years. There is a huge interest. You can see here you can interact with the virtual environment, and these motors on the top are squeezing your fingers by providing a force, because the platform provides the plane which is normal to the force, and the squeezing part provides the squeezing force on your fingertip pulp. So we are dealing with wearable devices that provides forces, not only vibration. Vibration was one of the standard and previous technology providing this kind of wearable interfaces. So we are able to do 5-finger interaction easily with the wearable device. Another important thing is the use of these technologies for teleoperation. Here you can see a device for medical robotics developed by DLR, where you can see that there is a grounded device that provides the console. And you have the master is a grounded device, and you control the slave. Of course, you have some constraint in the workspace. You don't have your free hand, so probably you will want to have the free hand to move the remote robot, the slave robot in teleoperation. So with this wearable device, now we are able to do teleoperation free hand with 5-finger by creating this. This is the setup that we have in our lab. We have 3 fingers actually here actuated, a lip motion that tracks the device, and here we have a DLR hand with the torque sensing, so you can measure the force at the fingertip, and this is the platform that is controlled by our motors on the nail, You can see how natural is the interaction because you move the hand is tracked and is displayed to the robot. So the robot does the motion that the hand suggests through the guidance. And then the force is measured here and is displayed on the 3 fingertips by using this platform, moving and showing forces at the fingertip. Free hand in this case. One of the problems here is that here it's quite anthropomorphic, the hand, but it's displaying only 2 contact points, while here you can see 3 interaction points. So there is a problem here in general, where you have a multiple finger on the master side, while on the slave you can have 2, 3, 4, 10 contact points, because the grasping part is completely different from what you want to do on the master. So we were also studying recently, we were also really interested to understand how to map the action of the human hand onto general kinematic structure that provides some grasping task. And we were abstracting, of course, when you have 5 fingers on the left and 3 fingers or 100 fingers on the right, you cannot do finger-to-finger mapping or joint-to-joint mapping, because the number of joints of the human hand is completely different from the number of joints of the robotic device. So you have to abstract something at the task level, at the object level. But the object can be any, and indeed this object does not exist for the human hand because the hand is free motion. So we were working with a virtual object, that was able to grasp the 2 main important things in grasping, that is controlling the internal force, which means squeezing, and then moving the object. So you can see this virtual object that is the minimum volume sphere that keeps in all the interaction points here. We call these interaction points because these points are supposed to have the force feedback wearable device on. So they will show contact forces. On the other side, you will have really contact points when you have the device. And so mapping these 2 spheres, you can have the nice mapping here. It's not wearable, but it's really, really nice because it's cutaneous. I don't know if I was clear before, but typically haptics, no, not typically. Haptics consist of force feedback kinesthesias plus cutaneous. Cutaneous is very informative. Now, you know this is the Da Vinci system. The Da Vinci system has the force feedback, also because it's really difficult to put in the loop the kinesthetic feedback and to satisfy the stability of the control loop. So we were doing this with the cutaneous devices. We were embedding our mechatronic device in the console of the system to show the force that has been captured by a biotach sensor interactive with a phantom organ on the other side. This was a work done with the group of Catherine Kuchenbecker. In particular, we provided the idea of the wearable cutaneous device. She was adding the voice coil on our platform to have both indentation of the cutaneous part and vibration. You can see how easily, and we got actually last year the Intuitive Surgical Technology grant for this research. and we went on January to present our result to Silicon Valley. So you can see you touch on the left, you measure, and you display on the right with our wearable device. 3 motors on the top, cables, and platform steering, providing force feedback. Again, the force is the orientation of the platform for the normal direction. The normal direction is the force, and the squeezing part is how strength is your force. Good. This is something that we are really happy to do. One of the problems was that this was very informative, like 18 measurements here. On the other side, you have only 4 variables, 3 of our motors plus 1 for vibration. So there was also here a very interesting part in mapping from multi-sensors to very few degrees of freedom. One of the problems here in palpation is very important because when you do cancer surgery, you consider a lump. So if you have a tumor, if I have a tumor in the lump, then during the operation, then the lump, there is a deflation, so there is no air inside anymore. So you don't know actually where the tumor is. So you have to palpate to find it. So it's very important, palpation in some application. Well, another important thing now is how we go to the convergence from wearable haptics to wearable robotics. So wearable robotics, actually there is my student here, Irfan Hussein, who is developing most of this work. He's wearing a wearable device on the left hand. Can you, no, yes, left hand, the wearable device. On the right hand, there is an extra finger, and we will show you how this works now. In particular, we are assuming, simulating that Irfan is a stroke patient. Well, this is a stroke patient. Alessandro is working with us since many months, and you can see how Alessandro cannot move the hand anymore, so he cannot grasp the hand. Of course, he has the left hand is working, but he cannot do any more bimanual tasks. It cannot open the bottle unless he does some strange maneuver, like putting the bottle under the arm or between the legs. So what we invented was this extra finger. So what was the idea? So a stroke patient cannot use the hand anymore. Okay, I cannot use an anthropomorphic robotic hand, for sure. And I don't want to use the huge exoskeleton to recover the motion of the hand. So what is missed to do the grasp? I mean, I have a part. This is like a palm, even if it's not working anymore. I just need an additional finger that is working. So the minimal robotic complexity that they need to add is a robotic finger. Adding a robotic finger that let him to have a new grasp with the part of his hand and the robotic finger to create this nice task again. So he's able to use the hand anymore with a very beneficial part for the arm. And this started with a master thesis in 2011, and is going to be published. Last year we got also, we were not winning, but was the first time that we entered the rehabilitation robotics community, and we get close to the award. So there are 2 groups working on extra limbs. One is my group in Siena and IIT, and the other group is by Harry Asada at MIT. And we started with the parallel and independent ideas. We started with this thesis in 2011, and we started focusing on application of stroke patients, where basically the hand is really playing a role in the grasp, and you are also really stressed by the wearability, as I told you. While Harry Asada started focusing on augmenting the human abilities with these very nice, fully actuated hands, fingers, that complements the hand work in doing manipulation. So it's really nice to have these 2 groups working on this. But as I told you, we are stressed by wearability. Also in this case, we want to have this extra finger wearable. So we realized a design where this extra finger becomes a bracelet, and the bracelet is passive because at least the doctor, so he is under his jacket, he creates this finger, goes in docking position, and he's able to, to grasp after. So the finger, a few details, is under-actuated, so we have flexible joints, we have a single motor, so it's compliant. designed the bending of the finger according to the minimum radius of the object we want to grasp. So we have some mathematics for grasp the object, and also we have some control that takes rid of the This is the convergence now. The wearable device is providing control for the wearable robot. So this is the confluence. So there is a switch. The switch is activated by the subject that starts with the finger. Get ready to grasp. And now he's doing a bimanual task. So he's using the paste again and the toothbrush again. So now I will show, if I give me 1 second, I will show how Irfan is going to grasp the object again. So he's steering with the left hand with the wearable device, and now he realized the grasp, and he can do any task he wants. And I can really do something very strong. It's really powerful, the motor. It's a servo motor, and he's also providing force feedback on the left. So so there is a force sensor, and the force sensor on the tip provides force feedback on the left, because when you have a stroke, you can also have hyposthesia, so you are not able to feel anymore. So if you don't know if there is enough force on the grasp. So you need a force feedback to understand if there is enough force, because this is not able to perceive anymore because of the stroke. Okay? Thank you, Irfan. Also for your work, of course. And this is the confluence, as I told you, and this is a patient doing, an hyposthesia patient, and he's having feedback on the left, and then when the feedback is provided, so he left the object with the arm. Otherwise, he does not know if the grasp is stable enough. Okay, then we have also some test. There is also another really beneficial. This was with the stroke since he was born, and there is a grasp device that is compensatory for the hand, but is really beneficial for the arm, because the arm starts moving again. If you have a grasp ability, you move the arm again. So it's rehabilitating the arm again. And we also have very nice work. He's preparing the jam and the bread, so you can see all our clinicals that are, actually they were happy in the videos showing the things. And he was preparing putting the jam on the, and he was also able to control. In this case, he has the hat to control. You see here there was some force control was wrong, and the piece of bread was broken, but now it was fine, and he was able to do this task. Also, this is also very nice. He was grasping an apple and cutting the apple again. It was involving part of his arm. Okay, so the body was part of the task together with the arm. So it's a really human-robot cooperation. Well, to say is that we can also have, we have one single motor, two more stable finger to grasp, so we can do more heavy tasks, like bringing a bag. You know, he said here for the first time, he said, he was saying in Italian, no. He said, davvero, you think it's the first time that I am lifting the bag with my arm. So you know this what it means for me, because you have this robotic hook in the. You can see here there is one student of mine blinded, so he's a high closed. There is a wearable device, and he is following a trajectory with the forearm. Okay, so he does not know that he has to follow this 8, but he's able to follow the 8 by using our wearable device, providing forces on the forearm. This will be really nice if you have a robotic arm and a human hand, and you want to do some cooperative task. So you have a supervisory intelligence that provides steering both on the robot and on the human to do some cooperative task, like grasping. Going to the very end, so this was the detail of the, so this is my idea, this is the end. So we want to create a new wearable device to have a better integration with the robot, and also to invent novel paradigms of interaction, and the 6th finger was exactly one of our best. So this is my group, and I want to thank all the people working in my group and all the projects, European projects, that are supporting us. Thank you.
we have time for a couple of short questions.
Yes? Okay.
On the fingertip haptics, how many degrees of freedom force feedback do you think are needed?
So we have three. Okay, we have three. But I learned that most of the perception is close to the nail. Okay, close to the nail. So I think that this is more informative because it takes information both this part and this other part, while this other part is less information because it's mainly only on one part of the nail. So I think that we are more suited, better designed to feel, of course, pressure, so wound off, plus this lateral stress more than this other one. So I think that if we have to reduce from 3, we have to go to 2. Like normal indentation and tangential in this direction. And this is what we did for the ring, and then I will tell you. There was another question there?
Yes, here. Can you hear me?
Sure.
Yeah, okay. I have a question regarding squeezing the finger to represent contact with objects. If you're touching an object, you feel a force, a resistive force, but in order to represent that, you squeeze the finger. So it's a different thing.
No, it's not a different thing.
What
It's
I mean by this is, if I move my finger and I have your device on
Yeah.
the finger, and then I feel the squeezing because I touched a virtual object, I can still move my hand.
Yeah, so if you zoom my action now, like my motion, slow motion. At the beginning, I do exactly what I'm doing with my device at the beginning. I squeeze my fingertip out, and then I go to the muscle and tendons. So I'm not doing something different. I'm just taking the initial part of the interaction, which is the cutaneous deformation. And I'm missing all the kinesthetic part. For sure I'm moving, but there is something in my brain that stops me. I'm not sure that I will stop, but there is something mechanically, but there is something in my brain that stops me. And this is the reason why we are really, so it's not a sensory substitution, because we are really there with the thing. And it's like with the headphone. With the headphone, you can hear high frequency very well and not very well the low frequency, and also because of wearability, you are missing something. Okay? But you're right.
All right. Let's thank Domenico once more for a very exciting
Thank you very much.